Hi, everyone! Welcome to the third episode of the video series about evolution from traditional VPN to EVPN. This episode focuses on how to smoothly evolve from VPWS+VPLS Interworking to EVPN VPWS+EVPN VPLS Interworking. First, let's take a look at the network diagram before evolution. Before evolution, an ACC is dual home to AGG1 active and AGG2 standby through LDP VPWS, and VPLS is deployed between AGGs and MCs. We're aiming to evolve the current network to one with EVPN VPWS plus EVPN VPLS interworking. The overall evolution roadmap is as follows. First, evolve from VPLS to EVPN VPLS. Second, evolve from VPWS to EVPN VPWS. Third, delete VPWS and VPLS configurations after network-wide evolution is complete. Note that, first, the recommended steps must be strictly followed during evolution. Second, all devices must be Huawei ones to support smooth evolution. They help ensure that smooth evolution performance requirements can be met. Now, let's take a look at the configuration in each evolution step. The NetEngine 8000 is used as an example to demonstrate key steps. Step 1. Configure evolution from MPLS VPLS to EVPN VPLS over SRv6 on AGGs and MCs. If only MPLS can be deployed on some devices, EVPN VPLS and VPLS can coexist in this scenario. We'll use the evolution from VPLS to EVPN VPLS as an example to describe the configuration procedure. Before you start, ensure that basic SRv6 and EVPN configurations have been deployed on AGGs and MCs. For details, see the second episode of this series of videos. The evolution procedure consists of the following steps. First, configure EVPN globally on MC1 and MC2. We'll use MC1 as an example to describe the configuration. The configuration of MC2 is similar to that of MC1, so we'll omit it here. Second, create a BD on AGG1, AGG2, MC1, and MC2, and set the BD to be in the evolution state. We'll use AGG1 as an example to describe the configuration. The configurations of AGG2, MC1, and MC2 are similar to that of AGG1, so we'll omit it here. Third, bind all AC interfaces of the VSI to the BD on MC1 and MC2. Let's use MC1 as an example. The configuration of MC2 is similar to that of MC1, so we'll omit it here. Fourth, bind the VSI to the BD on AGG1, AGG2, MC1, and MC2. We'll use AGG1 as an example to describe the configuration. The configurations of AGG2, MC1, and MC2 are similar to that of AGG1, so we'll omit it here. Fifth, configure an EVPN instance on AGG1, AGG2, MC1, and MC2, and bind the EVPN instance to the BD. We'll use AGG1 as an example to describe the configuration. The configurations of AGG2, MC1, and MC2 are similar to that of AGG1, except that their EVPN source IP addresses and RDs are different. After VPLS evolution is complete, you can find on MC1 that services have been switched to EVPN VPLS. Check MAC address learning on AGG1. The command output shows that the learning is normal, the newly created BD is displayed, and peer IP is SRv6 VPN SID. After VPLS evolves to EVPN VPLS, VPWS interworks with EVPN VPLS. The VPWS service status remains unchanged before and after the evolution. If evolution to EVPN VPLS is not as expected and a rollback to VPLS is needed, perform the following steps to roll back EVPN VPLS to VPLS. First, unbind the EVPN instance from the BD on AGG1, AGG2, MC1, and MC2, so that the services on AGGs and MCs are switched to the VSI and the broadcast domain is switched to the BD. Second, unbind the VSI from the BD on AGG1, AGG2, MC1, and MC2. Third, unbind all AC interfaces of the VSI from the BD on MC1 and MC2. Check whether MAC address learning is normal on a GG1. If VPLS is displayed in the command output, the rollback is successful. Step 2. Evolve ACCs and AGGs from VPWS to EVPN VPWS over SRv6. Before the configuration, ensure that basic SRv6 and EVPN configurations have been deployed on ACCs and MCs. For details, see the first episode of this series of videos. The configuration can be divided into the following steps. First, set the DF election delay to 0 on AGG1 and a GG2. This helps prevent traffic interruption caused by the long-lasting standby state during switchback. We'll use AGG1 as an example to describe the configuration. The EVPN enhancement port 60000 command is used to prevent ACCs from receiving duplicate BUM traffic after the backup DF recovers in a dual homing scenario. The same UDP port number must be configured on AGG1 and AGG2. It is recommended that the same UDP port number be applied on the entire network. The configuration of AGG2 is similar to that of AGG1, so we'll omit it here. Second, configure EVPN globally on the ACC, AGG1, and AGG2. Let's take a look at the global EVPN configuration on the ACC. First, run the remote VPWS FRR enable command on the ACC to enable remote FRR for VPWS EVPN. Then, run the PW extend private enable command to enable EVI AD routes to carry the L2 VPN PW private extended community attribute. This enables the AGGs, which are interworking devices, to associate EVPN VPWS with VPWS PWs based on the L2 VPN PW information carried in these routes. During EVPN VPWS service creation, the VPWS PW service is set to down to prevent the ACC from receiving duplicate BUM traffic. Finally, run the timer migrate delay 300 command to set the delay for switching traffic to EVPN VPWS to 300 seconds. Then, after EVPL entries are created, traffic is switched to EVPN EVPL after a delay of 5 minutes by default. The global EVPN configuration on AGGs is slightly different from that on ACCs. Let's use AGG1 as an example. Run the MAC redirect compatible enable command on AGGs to enable global MAC redirection, so that traffic from AGG1 to the ACC can be redirected to AGG2 if the link between AGG1 and the ACC fails. The configuration of AGG2 is similar to that of AGG1, so we'll omit it here. Third, configure EVPN and EVPL instances on the ACC, AGG1, and AGG2. Let's use the ACC as an example to describe the configuration. The configurations of AGG1 and AGG2 are similar to that of the ACC, so we'll omit it here. Fourth, on AGG1 and AGG2, bind the EVPN EVPL instance to the BD, configure an ESI for the EVPL instance, and configure ESI-based single active. This ensures that the AGGs can support preference-based DF election. Let's use AGG1 as an example. Note that an ESI needs to be configured for the EVPL instance only when the ACC is dual-homed to AGG1 and AGG2. Also note that the same ESI must be configured for AGG1 and AGG2. The configurations of AGG1 and AGG2 are similar, except for the preference-based election configuration. Because a larger preference value indicates higher priority, AGG2 is configured with a smaller preference value as the standby device and has a lower priority than the active device AGG1. Fifth, bind the AC interface to the EVPN EVPL instance on the ACC. You can find that VPWS and EVPN VPWS services coexist on the interface. Finally, after VPWS evolution is complete, you can find on the ACC that services have been switched to EVPN VPWS. On the ACC, you can find that the EVPL status is up, and the active standby AGG status is normal. On the ACC, you can also find that the VPWS/PW status is down, and services have been switched to EVPN. On AGG1, you can find that from the command output that MAC address learning is normal, the BD is displayed, and peer IP is SRv6 VPN SID. If the evolution to EVPN VPWS plus EVPN VPLS interworking is not as expected and a rollback to VPWS plus VPLS interworking is needed, strictly follow the rollback steps below. The rollback roadmap involves rolling back access devices to VPWS and then rolling back aggregation devices to VPLS. There are two VPWS rollback methods we can use. Let's start by looking at the first rollback method. Note that we need to strictly follow the rollback steps. First, unbind the AC interface from the EVPN EVPL instance on the ACC. Second, unbind the EVPN EVPL instance from the BD on AGG1 and AGG2. The second rollback method involves the migration rollback L2 VPN command. The rollback steps are as follows. First, configure the forcible rollback command on the ACC. Second, configure the forcible rollback command on AGG1 and AGG2. Finally, check the VPWS status on the ACC. The command output shows that the VPWS status is up, and the active standby AGG status is normal. For details about how to roll back to VPLS, see the preceding description about how to roll back EVPN VPLS. Step 3. After network-wide evolution is complete, you can delete VPWS and VPLS configurations in any sequence. First, you are advised to start by deleting the VSI configurations on AGG1 and AGG2. After the VSI is deleted, the L2 binding VSI 601 command configuration is no longer present in the BD. The configurations of AGG1 and AGG2 are similar. Let's use AGG1 as an example. Then delete the VSI configuration on MC1 and MC2. After the VSI is deleted, the L2 binding VSI 601 command configuration is no longer present in the BD or on the AC interface. The configurations of MC1 and MC2 are similar. Let's use MC1 as an example. Second, delete the VPWS configuration on the ACC. The ACC's AC interface is unbound from the VPWS accordingly. After the VPWS configuration is deleted, check the configuration on the AC interface. Finally, check whether the EVPN service status is normal on the ACC. If the EVPL status is up, the EVPN service is normal. Check MAC address learning in the BD on AGG1. The learning is normal. We've now completed all configurations for evolution from VPWS plus VPLS interworking to EVPN VPWS plus EVPN VPLS interworking. Thank you for watching.